Well, we're going to talk about the Jovians, so Jupiter and Saturn today. And then we'll do Neptune and Uranus. And then if we make it through both of those, which I hope we can, we'll have a little bit of time to talk about all the things that we skipped over, like very different moons and the rings and the asteroid belt, stuff like that, before we close down this whole operation. I'm scared, though. If it's already getting light, I'm scared nobody's going to be here on Tuesday. It's going to be very sad. We'll be talking to a camera. All right. What did you guys think about Mars last time? What's some thoughts? Yes.
The idea of the large gash in the side of Mars being like, we talked about that one guy in theory about Venus.
The Velikovsky, yeah.
Yeah, I found that really interesting.
We should note that most scientists hate this idea.
Well, I mean, I see why. Like
Yeah.
Venus moving through the solar system like that. But it is, I don't know. Honestly, I should have gone home and looked at it, looked it up, see what other theories are. But it seems very compelling because it doesn't seem like a canyon like that would have, with no outlet, would ever be created.
Yeah, let me see if I can just pull a picture of it really quick. It's a really weird feature, I agree. I've never been totally satisfied with any of the explanations that are given. Let me see. It's also, by the way, it's like the size of the United States, which is really crazy. This is kind of a cool picture. Let's see if I can pull this up. We can zoom in on that. It's not very dark. The screen is not ideal. But it is a heck of a scar. Yeah, there's nothing else in the solar system that really looks like that is the thing. Right? We see a lot of shared features, you know, the cratering, mountain building, volcanism. Where'd my mouse go? But nothing quite like that one, which is pretty weird. I always lose my mouse when I go around to this screen. It's a nightmare. Yeah, so you can check it out. Velikovsky wrote this book called Worlds in Collision. I mean, what's really interesting to me about some of this stuff is that, you know, people kind of scoff at it today, like these ideas like Hapgood's crust slip theory. Who else have we talked about? Carey's expanding Earth. Velikovsky's another one. But what people don't realize today is that when those guys were, let's say, contemporary, when they were, you know, in their day and age, they were taken very seriously. Like, Einstein wrote the foreword for Hapgood's book on crust slip theory. He also had this book on his desk at the time of his death, the Worlds in Collision book by Velikovsky. And like I said, Carey and Wegener were squaring off about the expanding Earth versus the kind of Pangea thing. And actually at the time, I always get these guys' names mixed up. Wegener was kind of the fringe quack at the time. And his idea is obviously popular now with the continental drift thing. So, you know, even at least in a historical perspective, it's interesting to think that these ideas were actually taken quite seriously at the time. You know, and it's hard to see that in retrospect because people are so dead set in their theories at the moment. But those will all change too. I'm sure whatever astronomy classes in this classroom 100 years from now will be very different than the one we're teaching today. Or at least the popular theories will be different. So yeah, I hope that's the one thing you guys take away from this course if you get anything out of it. These stories are always on the move. So that's a really weird one. Valles Marineris, what a bizarre feature. Really does look like somebody dragged its fingernail across the side of the thing. What other thoughts from last week? Yeah.
Before last class, I was thinking like, especially after the documentary, like all about like what if scenarios in like science and like I think Bell in the documentary said like you can't consider like every what if in science because it kind of holds science back. But when you talked about last class, like the idea of taking like stuff off of Mars and bringing it to our planet because we don't know like what kind of microscopic organism might metabolize this or do anything like get us sick or anything. It kind of put a different thought in my head like maybe we should question a lot of that stuff.
Yeah, it seems to me like there's a really fine line at all times for all exercises of human activity where we're trying to balance this chaos versus order. If everything is possible, then it's just complete chaos and you can't make a plan. Like you don't know whether to go out to the grocery store because you might get hit by an asteroid or something, right? But if things are too orderly, then there's no chance for development. It's a really interesting thing, and you see it in societies too, right? Like if societies get overly ordered, then you end up with something really totalitarian, like very fascist government essentially is like a really ordered government. But if things are like too whatever, then you just have complete chaos and anarchy too. So it's like, it's very difficult to strike that balance, and science is one of those places where it's really convenient to close the lid on things and be like, we got it, we understand this. But you have to keep at least some little 1% possibility in your mind. It's kind of like having a fight with your girlfriend or whatever. It's like, you need to remember there's like a 1% chance you're wrong at all times, right? Even if you're 100% convinced, it's like, wait a second, like, you gotta find that 1%. So there's something really interesting to that inability. You know, it's funny, I see it all the time too. Like there's some sort of chemistry program after this class now. And I was packing up after one of the classes recently, and the chemistry professor was explaining to the students how when you split light using a prism, like she was talking about black body light, but she was just saying when you split like a light, you get these colors, you get a rainbow of colors, right? But you never ever get pink or cyan or magenta, basically, from a prism. So she was saying these are not natural colors, they're basically illusions that are made by the combination of different gas lines and stuff. And I was like, I've heard that before, and I was thinking about it as I went home, but I started reading a bunch about it, and I realized, do you guys know who Goethe is? The guy who wrote Faust? Maybe you have to read that in classics at some point. He also turned out to be a little bit of a mad scientist in his off time, but he did a bunch of really weird experiments where instead of sending beams of light like Newton did through prisms, he actually cast shadows across like matchsticks and then sent the shadows through a prism. And when you send the shadows through a prism, you actually at the borders of the shadow get a completely different spectrum of colors, including magenta and cyan. Those are and yellow. So it's like yellow, magenta, and cyan are the three colors that split off the prism. And it's like, the entire color theory was based on Newton. I mean, Newton was a complete super boss. Yeah.
Well, cyan and yellow are real colors on the spectrum.
From a prism?
Yeah.
But not magenta. That's probably true. Yeah, definitely yellow. I don't know about cyan. Is cyan from a prism? I'm gonna show you guys a picture. I know where this is not. This is relevant because it's an interesting, like, just blind spot where I don't know that this idea has really been developed since Goethe. Goethean inverted spectrum. Let's see if I can show you guys a picture of this. It's pretty crazy. But yeah, there's always like cracks in the foundation of so many of these ideas that we think we have completely nailed down. Let me open this in a new window. I mean, the colors are kind of awful in this projector. Yeah, you guys probably can't see that. But you basically get like a pink and a blue one off the side of these shadows when they're cast through a prism, which is quite fascinating. Anyways, there's always more to the story than meets the eye. And I think that that's actually quite exciting. Other thoughts about Mars? By the way, I have no idea what to make this Goethean thing, but it's worth studying at some point. Mars, yeah.
I thought it was interesting about the moons. I never really considered Mars having moons.
Yeah.
We know that like Jupiter and like these planets with all their like fancy names and everything. And I thought it was interesting how one of them, I forget the names of them, but this kind of collides with Mars, and it's kind of the opposite of what our moon is doing.
Yeah, it's falling in. One of them's falling in, one's falling away, or flying away, however you want to look at it. They're like barely moons. It's very bizarre. I think we had like a school bus-sized moon that just joined our little orbit too recently, made some headlines. Yeah.
I don't know why I really downloaded that far. Why won't you show like the United States?
It's legit for sure. It's weird. It's really weird. Yeah, none of the explanations are super satisfying. I mean, if it's a cooling fracture, you would expect to see that on other stuff like the moon or Mercury. The water explanation doesn't really hold because there's no inlets or outlets for it. It seems to really be a gash in the thing. If you look at the Grand Canyon, it has an inlet and outlet, right? So the water is going from downhill up in the Rockies, essentially, and then coming out down in the, God, what is that place called? The Gulf of Cortez, I guess. It used to, anyways. There used to be a delta down there before we siphoned it off to build Phoenix and everything else. Yeah, Mars. What about moving to Mars? You give any more thought to that one, Dave?
I changed my mind. I don't want to do it.
You're not in for it? That's for somebody else, yeah. Not a very friendly place, but ambitious nonetheless. Yeah, some people are going to have to really suck it up if we're going to explore interstellar space, which seems to be the ultimate goal of all of this exploration. It's going to be rough. Yeah, thought.
Could we like make a dome
Yeah,
on the
on the
moon?
moon.
Yeah, like build oxygen like engines and stuff.
I think so. Do you guys know about, so they tried a version of this on Earth, actually. I mean, first of all, radiation is still a problem. I'm not sure how that would work out. There's probably ways to do it. But, so they tried, you guys know about Biosphere 2? Anybody hear about this? I actually, this is, okay, so there's this art troupe back in the 60s and 70s that was kind of like these eco-activists. They basically were like a bunch of theater kids who decided to get a sailboat and travel around the world back in the 70s. And the culmination of this little art troupe was that they decided, they got a bunch of money somehow, some billionaire, I don't think there's billionaires back then, but multimillionaire gave them a bunch of money. And they decided to do this experiment where they were going to build a self-contained dome system, basically, like a huge one that had all the different ecosystems of the Earth in it. It's really quite impressive. There's several documentaries about this. You can check them out. I think there's even one on Netflix. Biosphere 2. And the interesting thing about it was that they did have some technical problems. So the people locked themselves in it for, I think, 2 years. It was like 6 or 8 people. They did have one pretty serious technical problem where their CO2 scrubbers broke, I think, and they started getting really hypoxic, and everybody got really lethargic and had a really hard time basically doing all the work of farming and stuff they needed to do. But the bigger problem that happened was that they kind of started turning on each other. Especially because food obviously is really hard to grow your own food and stuff. I don't think there weren't animals for them to eat, so they were trying to grow their own food, and people got really hungry. So somebody or multiple people started stealing food from the shared pool, basically. And it got to the point where people were like hiding food, and like there was just all sorts of crazy treachery going on. But it's a heck of a drama to read about, because I think it is, in some sense, the test case for what it would be like to live on Mars or something with a small group of people. And it turns out that the biggest hurdles are not so much technical, but sociological, right? Psychological. Because how do you get along with 6 people for 2 years without any other contact, and you have to survive all together? It turns out to be a pretty tricky thing to do. It's an interesting story. I would recommend that documentary. We actually had one of the guys on our podcast, which was really fascinating to talk to him. But yeah, not going to be easy. But somebody's going to have to do it if we're going to ever get off this rock and check out other solar systems or anything like that. But yeah, I think people, like some of the big plans for, I think the Dream spacecraft is something like that too. That's like a self-contained ecosystem. I think that I did a calculation one time that, if you wanted to reach the nearest star system in a spacecraft that was moving like the same speed as our Earth is moving in orbit, that it would take you many thousands of years, like tens of thousands of years to reach that star system. Maybe you could go a little bit faster, but it's going to be many generations, right? It's going to have to be this intergenerational project, that's something to contemplate. Like, I don't know. Would you get on that one, David? That sounds a little more appealing to me than just being stuck on a rock. I'm like, at least we're going somewhere. But yeah, I don't know. Any more thoughts about Mars? Joe, got any thoughts? I'm glad to see you here, man. It's been yeah?
I have a question.
Yeah.
We were talking about, I guess, repairing or getting Mars's magnetic sphere.
Yeah.
Is it possible to juice our own magnetic sphere to make it stronger?
Why would you want it stronger?
I guess like solar wind like better protection to that, or
Or like as a backup or something? Yeah.
I guess it doesn't seem necessary.
It seems possible, yeah. I didn't have a chance, I didn't remember to go back and read more about that, but there's a Wikipedia page on it if anybody wants to check it out about the artificial magnetic field project for Mars. Seems plausible. You don't need a very strong magnet. I was actually, I'll get to you one second. I was trying to get to the bottom of like the strength of these magnetic fields, and they're all pretty weak. Like, I think, let's see, what was it? Jeez, I actually just looked this up. Like a neodymium magnet, you guys know like neodymium magnets, like basically the good magnets that you'd get to like stick something to your fridge or something. Those are on the order of like thousands of Gauss, right? The strongest magnetic field of any planet is Jupiter actually, which is like 4 Gauss. So it's like 3 orders of magnitude weaker than a refrigerator magnet, basically. So these are pretty weak. They're big and expansive, but they're pretty weak. So you don't need that much to deflect these particles and these ionized atoms and stuff because they're so little. You don't have a lot of momentum. So yeah, it's a good idea. Maybe we should try it out on Earth. I'm a big fan of trying everything out on Earth before we fly off somewhere to try and set up shop millions of miles away.
Well, it could also,
Oh yeah, go ahead. Go ahead.
someone else,
Along that thought, yeah.
okay. Well, it's just that, I mean, we talked about in the past how the magnetic field might flip. And it
Exactly, yeah.
happens. When it does, it weakens.
Right.
So it would be like, especially if that might happen anytime soon.
Yeah.
it'd be a really good time to not only test it, but, you know,
I agree.
test it.
Yeah, I agree. Especially coupled to the fear of the solar storms and stuff that people are. I know NASA's taking that really seriously right now, like how to defend against solar storms that might be really bad. But yeah, if we don't know how long the magnetic field goes down for during a reversal. Could be 5 minutes. It could be 100 years. It's just impossible to tell from the record. So yeah, that's interesting. Yeah, I should read more about that. We should all read more about that. Check it out. Maybe we can talk about it next time if anybody looks it up. I'll try to remember. Yeah,
I'm glad you went first because I'm backtracking. But
that's cool.
what, instead of doing like the intergenerational project thing, what if you just like froze some dudes?
Ah, the hibernation method. Yeah, it's not there yet. That's the bottom line. It's not possible to preserve. I mean, that'd be a cool project to try on Earth, first of all, and many people have done it already. So I think back in the 70s and 80s, this became a really popular thing to have your brain freeze when you died. I think Walt Disney has done it, actually. There's a few very famous people who have tried this out.
Is he actually? Is it that?
Is it true? Is it just an
Like,
Say they have his head.
urban legend? I don't know. Sorry, I shouldn't just say stuff. But it is definitely a thing you can actually pay for and have done, for sure, with the hope that one day people will figure out how to reanimate it, reanimate you. But yeah, nobody's figured that out yet. But it is the hinge point for many a sci-fi movie. But yeah, if you could figure that out, that would certainly work. It might be kind of sad though, like if you went to sleep for 40,000 years and then when you wake up, you know, the Earthlings are no longer there and you're on a. Yeah. Most of those sci-fi movies end dismally with. I saw one recently. It wasn't that good of a movie, but the guy was kind of going crazy going through these hibernation cycles. Yeah, I don't know. That's interesting. Yeah.
This is kind of off topic. It's not about Mars, but like, I have a question about the weather.
Okay.
How do they, how do they measure how many inches of rain there is, and how do they know, like, over a specific area, like they have to take an average, and like how many measurement devices would be set up within a certain area, like if it's like a desert.
Yeah.
It's a huge area.
Yeah, I think I've seen these things you can buy for your garden that are just cubic square inch things, right? And they just measure how
I
much.
just feel like that's a weird way to measure how much rain there is.
Yeah, I'm not the guy to ask. Yeah, it is weird. I think it's funny though how whenever we get these like, they're like this huge storm is coming, it's gonna destroy Oregon or whatever. It almost never happens. I think it's really interesting. I think a lot of this is just kind of like clickbait driven terrorism of some sort. People are just like planning the worst case scenario so that you'll click on their stories or whatever. But yeah, this storm didn't turn out to be too bad, huh? Even down in California, it's not that bad. So I don't know. It's weird. Any final thoughts about Mars? So we're gonna leave Mars behind. I want to talk to you guys about. I want to talk with you. You guys have read the textbook already about the giant planets. These are actually, in some sense, these are probably the most interesting in terms of. For me, they're interesting because I have pointed out to you guys a lot in the past that there seems to be this evolutionary metamorphic paradigm that's kind of making itself known in the planetary sciences community. And so two of the interesting pieces of the puzzle are going to show up. One being the really interesting and compelling relationship between stars and Jupiter-like planets, which essentially have very similar composition, but they're different sizes. And we're going to talk for a minute in a second about the brown dwarfs with a little more detail, because they're kind of the interesting missing link between those systems. And I'm very personally intrigued about the continuum there that we see expressed, which is a bunch of hydrogen and helium in one place, sometimes more of it in one place than another, and you get a very different outcome as a result of it. And the other one we're going to talk about next time is the continuum between Earth-like planets and Neptune-like planets, which is really interesting. So I want you guys to be thinking a little bit about this metamorphic selection idea too. It's really interesting because like the most famous theory we have in biology is Darwin's natural selection idea, but Darwin was not a scientist, right? He was actually, he went to divinity school and he got a job after that. He was from a wealthy family and he never seemed to fit in. I think he tried to go to med school for a minute, that didn't work out. Didn't work out at divinity school, so he got a job on a boat as a naturalist because he could read and write and draw pictures pretty well. And while he was on this big long trip, he started to just develop this kind of harebrained idea that, different species seemed to have some relationship to one another, and that if they were isolated on different islands and so forth, they might change over time in accordance with their environment, and you would get eventually the appearance of different what we call species, which is a really nebulous word still, but basically different looking critters. And I'm really intrigued by the same principle in some sense being applied to astrophysical bodies as well, where depending on the place where it develops, depending on the environments that it's exposed to, a certain body may end up looking like this kind of planet, that kind of planet, a star even, or just a big pile of gas and molecules. Right? We have these huge molecular clouds, which we'll get into next semester. So that's kind of the preface for a lot of the discussion we're going to talk about today. Oh, I did want to mention, I dug this up, by the way. This is the guy who's leading the Da Vinci mission to Venus that we interviewed. If anybody wants to check that out, it's number 142. But anyways, so we have these overlapping terms. So we got suns, we got really low mass stars, brown dwarfs, Jupiters, and all the way down. And then, of course, we have the icy giants, which we'll get into next week. And they are all really on quite an interesting continuum. And the Soviets, by the way, developed this idea of this metamorphic idea a bit more than we did in the West. So as you guys read in your textbook, I'm sure, the basic idea for the formation of Jupiter-mass planets and brown dwarfs and suns, for that matter, is this kind of accretion idea where you get a bunch of gas in one place, it sort of pulls itself into a ball, and you get certain outcomes. And of course, in the case of the solar system, a lot of the Jupiter-mass, the original idea for Jupiter-mass planets was that they were kind of this leftover disk of material after the star formed, and they kind of accreted out of that. Which is like, it's an okay story there may be a time and place for that. But the Soviets actually had a little bit of a different idea, and there was this scientist named Oparin who wrote this book called Origin of Life. I'm sure there's a Russian name for that I can't pronounce. But Oparin's idea was that actually, as stars cool off, that they would go through this metamorphic chain where they sort of turn into something that looked like a brown dwarf, and then they turn into something that looks like a Jupiter, all the way down to looking like something like an Earth, actually, which was really, really radical. And the Soviets, of course, had like a very different cosmological picture too, because they were completely walled off from the West, so they weren't part of the same paradigm system as the West. Now, I think that most scientists today would not buy that for a second, but I do think that it's an interesting idea. And I'd say that the main reason that we don't entertain that Oparian idea today is because of the timelines that we have for the universe, which constrain its age to about 14 billion years, which is what I think like 3 times the age of the Earth, according to that story. So it's a very short amount of time in order to make things happen, certainly far too short for something to cool off. A star to cool off to the point of looking anything like an Earth or looking like most of the planets that we see today. But there's little intriguing kernels of it, I think we're going to peel back some of those as we go forth today. And I think it's a really tantalizing idea, especially as we see the cosmology in the West shifting so quickly in terms of the age of the universe being expanded. It's getting older. The people are beginning to take seriously the idea that the universe is much older than we thought it was. And that will, of course, really open up the sea of possibilities of how we get a lot of the bodies that we see in the sky. So what else can we say about this? I mean, it's also worth mentioning, I wanted to point this out too. There was one really big study. It was called VASCO. So what was it? Vanishing Astrophysical something objects. Basically, there was this study done where these scientists took a look at all of these frames from the sky across like 50 years. So they got this US Navy database of just these telescopes. I don't even think they were telescopes. They were just shots of the sky across, the same picture of the sky across many, many years. And they noticed something really strange, which was that a number of stars seemed to disappear, which is really, really weird because, this will make more sense next semester, but we have this pretty homogeneous view of the lives and deaths of stars. They kind of generally are thought to blow up, right? But we don't see that many stars blowing up. In fact, the last one we saw blow up in our galaxy was in the time of Galileo. So it doesn't seem like a very common thing that stars actually go nova. However, we have seen a lot of stars disappear, which is really, really weird. And so they go through, we actually had this lady who headed this study up on our podcast too, number 145. And it's really interesting because she tries to, her and her colleagues who are authors, they discovered something like 100,000 different objects that seemed to be mismatched across the years. So there was something there early on, and then over the course of the 30 or 50 year interval, they disappeared. And they were able to rule some of them out as maybe they were little lens flares or scratches or something, but there was a big body of these objects, a good volume of them that they couldn't account for. And so for me, I'm like, that's really fascinating that you do see some evidence of things that are at least changing in the sky in a sort of way that would be compatible with something cooling off in a non-destructive, non-explosive way, which is really, really fascinating. So, and I've made the case to you guys before that brown dwarfs, the kind of strange missing link, they're basically bodies that are the same size as a Jupiter, but they have a lot, they might be a little bit bigger in radius, but about the same radius as a Jupiter, but a lot more atoms crammed into it. They're a lot denser. There's something on the order of 10 to 80 times as dense as Jupiter. Same material, same hydrogen and helium as a Jupiter or as a sun, but not quite enough for it to kick into fusion. So those atoms aren't getting squished together enough in order to fuse at least neutral hydrogen. So something like a heavy hydrogen, deuterium, would be able to fuse on a brown dwarf. But so they're like almost stars. And anyways, I've made the case to you guys before that that's a really interesting threshold, that at some point you have enough, you just have one extra atom on that thing, and you actually have the ability for it to fuse neutral hydrogen. And at some point, if you take that atom away, you don't. And all of this points to a really interesting possibility, for me anyways, that that there is some sort of continuum between these objects, right? And it seems completely possible to me that the objects could spend their time in different phases of this life. Now, it might be more easy for a sun to lose atoms and cool off to look something like a brown dwarf than vice versa. Like, we don't see Jupiter gaining mass, for instance, right? But maybe under certain conditions, if it was in the middle of a giant molecular cloud or something like that, it would be possible that it could grow. And certainly our main story of how stars form, which we'll get into next semester in detail, is that something nucleates, right, which couldn't be imagined as anything other than a Jupiter-like thing, and it's just glomming on all of this hydrogen and helium and getting, spinning and getting more dense and so forth. So there is definitely this, that's kind of at the heart of our story for how stars form as it is. I just think that it's tantalizing to imagine that the story could play both ways, and at least holds up to rationality. I don't think we've ever observed anything like that, but it's very hard to observe any of these things on the timescales they occur. It's also interesting too because we only see stuff that's bright, right? It's very hard to see cold things that are out there, very, very hard. So we have observed some brown dwarfs, even though they're not glowing like a star. But the main way we observe them is in the infrared spectrum. And if something gets below a certain level of coolness, it's like you're not going to see that stuff. So we estimate, I think that there's something like 100,000 brown dwarfs in the galaxy. At least the upper bounds, but it could be even more. We just can't, who knows what we're not seeing. They're very cold and difficult to see. So there's also an interesting temperature continuum here. So you have a compositional continuum between stars and Jupiters, right? And the brown dwarfs are kind of in the middle, where they all share a similar composition with, you start to see, as you move down this continuum, you see that these guys are cooler, obviously, than stars, right? But they also start to, as they cool, they seem to develop more complex chemistry. So you start to see things like methanes and ammoniums and more complex molecules starting to form down here as these on the colder end. Whereas stars tend to be like really simple stuff, elements, just straight up elements, not a lot of chemistry. There's debatable chemistry in the coronas and so forth, but very simple elements, lithium, carbon, oxygen, and a lot of hydrogen and helium. So, interesting continuum there. There's also this continuum about the convection. So, what's kind of interesting is that when you have like a star, like a red dwarf, let's say, which is kind of just a cooler, smaller version of our sun, you still see a lot of it's considered fully convective. So the surface is really churned up and it's very homogeneous on the surface. So when you look at a picture of the sun, the surface, the photosphere of the sun, it's very homogeneous. Like it's a little bubbly and stuff, but it doesn't have these big, like, long streaky weather patterns like we see in our upper atmosphere or like we see on Jupiter, right? So there's something about it as it cools that it kind of loses that like real churny aspect to it. And so, the standard story is, of course, that these things all form under different conditions, but they also do seem to be very much on a continuum that would lend itself to a cooling process, which is quite fascinating. So if we compare their cross sections, it's kind of interesting. There's a brown dwarf down at the end. And by the way, so the reddish thing is this, well, it's metallic hydrogen. So I guess it's worth mentioning to you guys that they're called gas giants, right? Jupiter planets are called gas giants. Saturn, too, is a gas giant. They're not made out of gas, though, right? And this is, the term was actually coined by a science fiction writer, and it kind of stuck. But only the outer little crust of these things. So this is our Jupiter over here. Looks like what? Like the outer fifth or so of the radius is gaseous. Once you get down below that, there's so much pressure on that hydrogen that it actually takes on this really unique phase, which is liquid-like, and it has a newfound conductivity as a result of that, because the atoms are basically squished so tight that they share, their outer surfaces are indistinguishable, their electrons are shared. Now, metals are the same way, right? So, the reason metals are conductive is because their outer shells of their atoms are all kind of gummed up together. They're really indistinguishable from one another, and that's why they're so nicely conductive. The same thing seems to be happening on Jupiter. And this gets into a really interesting, this is actually a very, very recent conception. So if you would have, even 3 years ago when I first taught this class, the textbook cross-section of Jupiter, I actually haven't looked at the textbook this year, but the cross-section, if you would go to Wikipedia of Jupiter or something, would have had a liquid hydrogen, but it wouldn't have gotten into this liquid metal. They would have said liquid metallic hydrogen would have been maybe in the core, we're not sure. But in the last couple of years, they've been doing studies where they've actually been able to flash shock hydrogen and produce this metallic form of it under the pressure conditions that they expect on Jupiter. Now, why is that interesting or exciting? It's interesting and exciting because if you guys think way back to us talking about the sun, and if you stick around next semester, I hope you will, this is going to become central, is that the sun was originally envisioned to be this burning ball of gas too, sort of like how the gas giants were supposed to be gas. The problem that we pointed out before with treating the sun like a ball of gas is that its spectrum doesn't look gaseous at all, right? And if it's not gaseous, then that means that you actually have some sort of a more liquid-like character to it. And if you do, then when you're interpreting what stars look like in terms of their temperature, you have to actually consider the structure of that liquid. Now, most of us don't think about liquids as having structures, but they absolutely do. It's actually one of the big forefronts of biology right now is starting to look at the structures of water inside of cells and how those structures actually are used to do work and set up circuits within the cells. And the same process of structuring the actual materials inside is probably going to explain a lot of things for us down the road. So anyways, I wouldn't be at all surprised if the way that now we're thinking about the interior of these gas giants as this liquid metallic hydrogen is the way that we start thinking about stars as well in the very, very near future. It seems inevitable to me as far as weird ideas we've talked about in this class. I think that one's definitely going to happen. You guys have any thoughts about this so far? Brown dwarfs? Yeah.
So would it be like an ocean-like surface?
Kind of, but it's hard for us to imagine because the pressures are so absolutely unimaginable. But yeah, it is a liquid. It really is. So if you actually compress hydrogen inside of a tank, right, it will also turn into a liquid. You compress any gas, it'll turn into a liquid, which is really astonishing that people don't think that about the sun yet, exactly, at least not en masse, because the surface of the sun is supposed to be something approximating the density of water. And so if that was the case, it's hard to imagine how it wouldn't be in a liquid-like state. But yeah, if you compress it even more beyond that, it starts to take on this metallic-like property. So a liquid, the difference between a liquid and a metallic liquid is really just a matter of whether the atoms themselves still have individual identity to them. So it's kind of like this. If I took three of us and we went into an elevator, let's say, we'd have a lot of room to move around and stuff, right? We could kind of turn and talk and we'd be quite comfortable. If I crammed maybe 10 of us into an elevator, we probably couldn't move very well. It would be a little bit more restrictive. That's kind of like a liquid. Now, if I crammed 100 of us into an elevator, there wouldn't be much left of us, right? Basically, we'd all be goop. and we'd be kind of blended up together. And that's kind of what happens with metallic, metallized liquids, essentially. So their actual atomic surfaces kind of blend together at that point. Pretty weird stuff. So at any rate, you can kind of see there's a continuum here to some extent. The brown dwarf certainly has a lot less of the atmosphere component. It's definitely denser, and as you kind of move down this continuum, you get more and more to the extent that this is Jupiter. If you compare Jupiter and Saturn, Saturn's a lot less dense. It's a little bit more gaseous in its outer reaches, the yellow stuff. You also start to see the appearance of ice-like and rocky stuff. I guess that's present in Jupiter. This is still debated about Jupiter, whether it has a solid core or not. But you start to see, especially when you move into the Uranuses and the Neptunes, the ice giants, you start to see more complex molecules, like really interesting combinations of atoms for the first time. So, and those are, of course, natural cooling reactions, condensation reactions. So in some sense, it makes sense. Now, it could be that that these guys, because they form farther away, the standard story being that they form farther away from the star, maybe there's just more condensation possible and all of this more complex chemistry can happen. Could be that they're just older, too, and more evolved. So, yeah. I don't know what to say about this. The rotation periods actually track too. So there's a continuum of rotation periods amongst all of these. So, something, what is this? A brown dwarf over here has an hour-long rotation rate. The Jupiter takes 10 hours to go around. And then Saturn is a little bit slower. It's like a little more than 10 hours to go around. So there seems to be like an angular momentum association with this, where they fit onto a nice continuum as well. So you have a temperature continuum, you have a density continuum, and you have this rotational continuum, and also the convective continuum that I was pointing out earlier too, which is really just the kind of complexity of the weather patterns on the surface. Really, really kind of intriguing similarities and differences amongst all these guys. So we've got two of them, obviously, Jupiter and Saturn. And here I have it written down. So the word gas giant came from this guy named James Bleish, who was a 1950s sci-fi writer. Not true, but people liked it, and it stuck. Jupiters. Okay, so Jupiters and Saturns, and really even the ice giants we're going to get into, Uranus, Neptune, they are all considered Jovians, which is just means Jupiters, basically. And they fall into an interesting temperature continuum here, where you see the evolution of different complexity based on temperature. So we're looking at kind of from coldest to hottest over here. So these are generally considered types 1 through 5. So the coolest ones require the planet to either be around a cold star or to have formed in a distant orbit, or to be located, I guess, in a distant orbit when we're observing them. You would see the most, maybe more complex chemistry in those, so ammonia clouds, stuff like that. Water clouds could develop on the slightly warmer ones. You also see the appearance of methane and hydrogen at that end of the spectrum. Then as you move further away, you start to see more elemental dominance. So hydrogens, you even see elemental carbon. They think that there's actually like diamond rain on Saturn to some extent. Same goes for Jupiter. And then silicate clouds on the really hot ones as well. So again, another continuum of temperatures and complexity of molecules. We also see these really weird Jupiters, not in our solar system, but out there in the galaxy. These are called hot Jupiters, which is really interesting. These are guys that are so close to their stars that they're getting cooked. And I think I've mentioned these a little bit in the past. But many of them are losing their atmospheres at incredibly incredibly accelerated rates, right? So they're actually transforming in real time. They also seem to be often tidally locked to those host stars, so they're getting cooked on one side, kind of like Venus is, but they're of the giant star variety. Very, very strange and interesting bodies, the hot Jupiters. We see hot Neptunes as well, which is really fascinating. So how does that happen, by the way? So what the theories about hot Jupiters, a lot of them, by the way, have retrograde orbits, so they're not orbiting the star in the same direction as other planets, which for me, I think for a lot of planetary scientists, seems to indicate that they're kind of late joiners. Like whenever you see a planet or a moon going the wrong way around a star, you gotta at least start to think about capture mechanisms. Like this thing couldn't have happened at the same time as everybody else. It got here recently. It's not doing the same dance as everybody else. And so a lot of these hot Jupiters seem to have these sort of off-kilter retrograde orbits, which is really, really strange. More than half of all the hot Jupiters we've seen have orbits that are misaligned with the rotation axis of the stars. So interesting possibility for capture with those things. There's also, I should have pulled up the paper, but the James Webb recently found, I think, more than 40 pairs of Jupiters orbiting each other with no star in the Orion Nebula, which is really, really bizarre. And I think that this whole paradigm of planets getting captured or jumping between solar systems, I don't think we're quite ready for it as a scientific society right now, but I think that it's kind of making itself unignorable. Is that even a word? I think that it's hard to turn away from them at some point, especially when you see these hot Jupiters, which couldn't have formed right next to the star. There's no way, because the chemicals that are present in them require cold temperatures a lot of times, right? Especially some of these ammoniums and methane, stuff like that. They had to have formed somewhere cold and then moved close to the star, really close to the star. And some of them don't even appear to have, like I said, be orbiting in the right direction. So it's not like their orbits just shrunk or something, right? They seem to have come from someplace else. You pair that together with these Jupiters that are just starless out there, and not just one of them, but like a whole bunch of them, right? Then you have to start thinking about the idea that planets might spend time not part of a solar system. That's pretty crazy. That's not really part of our formation story right now at all. But it's really exciting too, because I think that it gives us the opportunity to come up with more satisfying explanations for a lot of the bizarre features we see. I've pointed out before that there's a period on Earth where the entire Earth was covered in 5 kilometers of glaciers, like the entire Earth, even the equator. And it's like, that's a really hard thing to explain based on precession or shift, tilting axis or almost anything, even like a volcanic winter. It's hard to imagine the equator getting so cold that it has 5 miles of glaciers. But if the Earth was spending some time at a different orbital location for a moment, or even not even in the solar system, then all of a sudden you have a situation where you could get things really, really cold for a while. And so, yeah, I think this discovery by James Webb of these solo planets orbiting one another is just super exciting and fascinating. And I imagine they're going to keep finding more and more and more of those. What do you guys think? Yes?
Is that like kind of, well, it's not confirmed that Pluto and Charon are like dual planet or dwarf planets orbiting each other. It's like kind of, that was just in the quiz.
Yeah, you guys are way ahead of this, yeah.
Is it kind of like that, where it would be 2 planets that are just kind of orbiting each other, just out there somewhere?
Yeah, but without a star, which is really, really weird, right? I think it's actually, I mean, for me, that's one of the most exciting findings of this whole latest generation of telescope, which is the James Webb. It's just, no one would have ever thought that even 5 years ago. It would have never been thought that we had this idea that there might be rogue planets that had escaped, right? That had been discussed in the literature, and there was some candidates, but the problem is planets are really cold for the most part. They're very hard to see. Jupiters are huge, so they're easier to see, but we weren't really able to see anything like that until this James Webb telescope went online. But the fact that as soon as they start looking for them in one little corner of the sky, they see like dozens of them essentially. It's just absolutely a game changer in terms of the stories that we have to tell about where did they come from. Like, you know, any story you can tell about how those got there is really going to change the our entire formation model of the solar system. Because, you know, if they formed in place from molecular clouds, well, then they're kind of like unformed stars there in some sense. If they got cast out of a solar system because they formed in the conventional story that we tell about Jupiter's forming, which is from this disk around the baby sun, well, then they left their solar system. That's really crazy too. Any way you cut it is super exciting and interesting and very, very different than anything that we had been telling. You know, I've mentioned it before, but it's worth pointing out that, again, the solar system that we have looks, generally speaking, nothing like any of the other solar systems that we're starting to see with these exoplanet explorer satellite projects. Like, almost all of those, definitely the majority, the overwhelming majority of those solar systems have really homogeneous planet types. Like, they'll just have a bunch, and it might be a selection thing, like we're not able to see some of obviously the Rockies are really tiny and stuff, they're gonna be hard to see, fair enough. But generally speaking, it's a very homogeneous solar system in all these cases. The planets are kind of one type, generally speaking of the super Earth or Jovian variety. And the whole solar system's like that. And they see this in solar system after solar system after solar system. Ours appears to be really diverse, on the other hand, lots of different types of planets in it. And so the story that we told for how solar systems formed was based on our solar system. And so now that we're able to finally see how other solar systems are, it's really forcing us to rethink some of these things. So, yeah, I just feel like this whole narrative is really on the move, and it's quite exciting. I think it's exciting, anyways. Thoughts, questions? All right, what else do we want to say about Jupiter? It's interesting to me. So Jupiter. You guys, Jupiter is essentially named, and it's worth pointing out that all of these planets are named after mythological characters, right? Which is like, on one hand, it's like, why do we do that? It's kind of weird. It must mean something important to us that we'd name them this way. What's interesting is that if you go all the way back, you know, so the Jupiter is the Roman name of the patriarchal deity, like the king of the gods or whatever. In Greek tradition, that was Zeus. And if you go back before that and you start digging down through like the Canaanites and you eventually get back to the Sumerians, you will find Marduk being associated with that planet, who is their kind of chief patriarchal deity. Now, it's really interesting because if you go out and look at the night sky, which of the planets is the brightest? Come on. Yeah, it's Venus. So why didn't they name Venus the king of the gods? It's really weird. Anybody?
Well, like, when were they named? Like,
I mean, this was like 5, 6, 7, I don't know how many thousands of years ago, yeah. I mean, Marduk is the oldest version of this, which is from the Sumerians. But they did, for some reason, have the foresight to, you could say it was an accident, but they associated the largest planet with the chief deity, even though it wasn't the brightest. Yeah, that's what I'm saying. How did they know? I mean, so there is something really interesting here. It's kind of a trick question. The planets, you know, the ancients considered all the planets stars. They were just wandering stars, right? They'd moved in unpredictable, well, eventually predictable, but different than the background stars, right? So if you take a telescope and you try to look at any star in the sky, turns out that you can come up with a brightness for that, but you cannot actually resolve the diameter of any star. So there's no apparent angular diameter of any star in the sky. The planets, on the other hand, have observable diameters to them. So if you're looking at a planet, the width of it is actually different depending on which one it is. And Jupiter does have a bigger angular diameter than Venus. So perhaps they were talking about the actual size of it rather than the brightness of it. So perhaps they did have like a pretty decent sense of the fact that it was a big body out there. What were you going to say?
Is there anything else to use like the orbit of it?
Mm.
Like if Venus was brighter, but it would be behind it and wasn't like.
Yeah, Venus is closer to the sun, right? So it doesn't spend as much time in the sky because it's always going to be closer to the sun as the sun's moving over the horizon. That's why Mercury is only visible for a very short amount of time when you can see it, which I think is where the whole messenger of the gods thing came from, because it's flittering around in the sky. But yeah, Jupiter does hang out in the sky a lot longer. It's probably one of the easier ones to catch because it's almost always visible as a result of being so far from the sun and being huge. So I don't know, for whatever reason, it seems like all of these Western tradition ancestors had it nailed as the king of their god system, which is really interesting. The Hindu astrologers called it like the chief guru, which is also kind of similar. Chinese called it the year star, which is interesting. So the Jupiter takes about 12 years to go around the make its orbit. And so I think the reason the Chinese called it the year star is because it would basically appear in a different zodiac symbol every year, right? There's 12, it would go through these 12 houses over the course, and they in some sense oriented their calendar around that. So Jupiter would mark the place, which is really fascinating. So yeah, I don't know how all these guys figured it out, but it is interesting that planets do have this angular diameter, so there is something appreciable about its size in like a width way that doesn't necessarily correspond to its brightness, which of course for Venus is because it's closer to the sun. It's closer to us too. So that's kind of interesting. All right. Jupiter, it's a fixation. We've been there a bunch. I mean, we haven't set foot on the thing because it doesn't really have a surface. But there's a bunch of different programs. I think this goes up through 2016, but there's 2 more missions that have been launched recently. You guys, I think, checked out a movie about Pioneer, which was one of the first flybys for this planet. That was back in '73, Pioneer 10. Got some nice pictures of it. Voyager flyby missions. Galileo was in '95, New Horizons 2007. Recently, I think, last year was the JUICE mission. What a name. From the European Space Agency. Jupiter Icy Moons Explorer mission. So they're actually going to set up an orbit around Jupiter and check out some of these moons, which I hope we'll have time to talk about because they are actually reasonable candidates for setting up little bases out there. There's also hope. There's some geysers that are popping out from the crusts of some of these moons, which is really interesting in Enceladus in particular, where people are hoping that we might see something like those vents with potential for microbes. So fun plus danger. We also just this year, NASA and the United States launched another mission called the Clipper, the Europa Clipper mission, with very, very similar objectives. But it's going to be a long time. It's going to be a very long time because those missions aren't even orbiting the moons themselves. They're just orbiting Jupiter and trying to take some nice readings of the moons as they go along. Jupiter's got a pretty serious magnetic field structure. Like I said, it's the strongest magnetic field in the solar system by a long shot. It's, I think, on the order of 3 orders of magnitude, 1,000 plus times our own magnetic field here. And it's got a really interesting system if we get a chance to explore the moons of Jupiter. If we run out of time, one of the biggest, so there's 4 big moons for Jupiter, right? They're called the Galilean moons because Galileo saw them through his telescope. Jupiter has, I think, 80 different moons actually, but we only really talk about 4 of them. And they're really big moons. One of them is this kind of volcanic monster. It's the closest one to the surface of Jupiter, the closest one in. It's called Io. And Io is just squirting out all of this material, all of this volcanic junk into orbit around Jupiter. And because it's this fine, misty stuff, it's actually getting ionized out there under the low pressure. And the result of it is that it acts as a kind of amplifier for Jupiter's magnetic field. So it sets up a charged circuit, almost like we were kind of playing with ideas about how do you make a magnetic field, where you can certainly amplify one if you have these charged particles in a predictable orbit. So you actually set up a circuit of some sort that has a corresponding magnetic field with it. So they think that part of the reason Jupiter's magnetic system is so strong is because of its moon's involvement in churning out these ionized dusts and stuff, which is really, really cool. Huge magnetic influence. It has visible auroras too. I don't know if you can see these through a regular telescope, but apparently they're quite incredible. 20,000 times stronger than Earth's auroras. Pretty incredible. Moons, yeah. So what's really interesting about its moons is that some of those moons, especially Ganymede, I mean, it's almost the size of a planet. If you compare it, it's smaller than Earth. That's the third one down over there under Jupiter. But quite a bit bigger. Let's see, where's our moon? Over there, right? So Ganymede's bigger than our moon, and the other 3 Galilean moons are kind of on the order of our own moon, too. They're all very, very different than our moon. Like I said, they all seem to have some sort of, not all of them, many of them seem to have an icy crust with what people believe is a subsurface ocean, hence the venting of all of that steam and stuff out into outer space. So interesting waypoint potentially for setting up bases and stuff in the future. I wouldn't be at all surprised if that's a stopping point on the way to the stars eventually, one of these moons over here. Saturn's also got a bunch of moons. We'll talk about Saturn a bit. Titan being the weirdest of all of those, which has this really mustard atmosphere and huge methane lakes and just a very, very bizarre object in its own right. All right. So if we look at Jupiter's moon systems, we have the Galileo moons on the interior, but we also have this whole series of moons exterior to the Galilean moons that are going the wrong direction, which is really, again, it really opens up your imagination when you see these retrograde moons in orbit. And when we go and look at Saturn in a second, we're going to see that Saturn's is even crazier because not only does it have prograde and retrograde moons, but it has off-axis groups of moons as well. So it's got multiple rings in all directions of moons. So you got to start to think that there's something really interesting happened at some points in the maybe distant past. But certainly this thing, certainly all these moons didn't just start where they are at, or something happened to drag them off of place. Late joiners or something. Very, very interesting. It's got those Trojans. I think we talked about those a bit. By the way, Jupiter, it turns out, I didn't even mention this when we were talking about why Earth is such a comfy place to live. It turns out that Jupiter does a really, really good job of, how would you say this? It kind of acts like a magnet, not in the literal sense, but it grabs up a lot of the junk that would probably threaten us. So you might ask yourself, like, why don't we get hit with huge asteroids every day or huge comets? Like, we do get hit by them, and it is a problem we should deal with, but we don't get hit by them that often. And people think that a huge reason for that is because we have Jupiter out there. So if you think about these comets, like the big chunky things that come in periodically and kind of randomly, they're hard to predict. They're on these big elliptical orbits, comets. A lot of those comets end up either getting grabbed up by the sun or by Jupiter. In fact, there was one in recent memory, maybe it was back in the 90s or early 2000s. They actually watched this comet just get completely gobbled up by Jupiter. It was really quite amazing. I wish I'd pulled a picture of it up now. What's it called? Shoemaker-Levy, I believe? I'm going to mess this up. Anyways, you can check it out and watch movies of it. But basically, the comet comes in, and it gets ripped apart by Jupiter's gravity, and it makes a bunch of little explosions. They're not little. They're like way bigger than atomic bombs, just exploding all across the surface of Jupiter. But it's thought that Jupiter acts in some sense as a net to grab up a lot of the stuff that would threaten us otherwise. So it's good to have a giant planet in your solar system, it seems like, if you want to have life. All right, let's talk about Saturn. Saturn's kind of on the same continuum. Obviously, the ring structure is worthy of examination. We'll try to do that. We'll try to give that its own attention here after Thanksgiving. But if we ignore the ring structure, which we don't want to do, we'll get back to it, don't worry. It is very similar in composition to Jupiter. It's also on this exact same Jovian continuum with the brown dwarfs and with the stars themselves in terms of composition and this onion layer structure that we start to see developing. So it's mostly hydrogen, helium. It's got a magnetic field, but it's relatively weak, like a 20th of Jupiter's magnetic field. The interesting thing, people from the density estimates are pretty well, they're pretty convinced that Saturn has some sort of a rocky core to it. I haven't read about this core discussion in the last year or two, so maybe this has developed beyond last time I looked at it. But the core of Saturn and the core of Uranus and the core of Neptune is really, really similar to the Earth in composition, which is fascinating. It's also the same size as the Earth, which is really interesting too, right? Again, we're still really struggling for a mechanism of how you get something as dense as the Earth to come together under its own weight. It's very difficult. You have that pebble boulder problem that just won't go away when it comes to accretion models of Earth. And so the tantalizing idea of cores being what eventually evolves into something like a rocky planet is really, really intriguing to me. All right. What else do we want to say about Saturn? Saturn has a little bit more, it has a little bit more of the complex molecules developing. It has ammonium crystals in the upper atmosphere, which leads to all sorts of interesting electrical patterning and lightning and weather. So there's little storms that develop. We have that storm on Jupiter, but it's much more stable and long-lived, right? So when I was a kid, they were saying that this red, we didn't even talk about the red dot on Jupiter, but when I was a kid, they were like, this red dot's been here for millions of years and it will be here for millions of years. It's actually disappearing like in my lifetime, which is really crazy. I don't think anybody saw that coming. Saturn has had a few of these little dot systems. Let me see if I'll come back to that. Yeah, so here's a little storm system on Saturn that was quite transient and only lasted a year in 2011. So there's something about Saturn which seems like it's a bit more turbulent and closer to something in the weather world that we would experience here on Earth, right? Than something like Jupiter, which seems a bit more stable. When we did this Cassini flyby with Saturn, they found that it had these really beautiful polar vortexes, this kind of hexagonal pattern at the surface, which was really puzzling, I think. But a bunch of scientists jumped on it at some point and realized that if you just rotated liquids in a vat, that you could actually develop this same eddy system inside of basically just like a washing machine type system, which is quite fascinating. Here's Saturn's moons, by the way, all over the place, right? Saturn's at the center, but you've got not only retrograde, not only prograde, but there's 83 moons, and they're all going in different systems. And you might think about each one of these systems as a different event, some sort of really interesting event that must have happened in the past, right? Because it's not like it just grabbed a moon up and grabbed a moon up there. Something discrete seems to have happened somewhere in Saturn's past, where it got an actual group of bodies several different times. It was just very, very bizarre. Well, I'm hoping we'll have time for Saturn's moons in and of themselves in a little bit here. So, yeah, what else can we say about Saturn? The rings are disappearing, so you've lost your chance. They're not disappearing, but they're going on their side, so we won't be able to see them for the next couple of years. It's actually really fun. In addition to seeing Jupiter's moons, you can see Saturn's rings through through binoculars if you put them on a tripod so you don't jiggle them. All right, questions, thoughts?
I've read into Saturn's moons a little bit. I guess now that I know a bit more from this class about there's a point at which when you get close to a planet that it's basically gonna like rip a moon apart, or like it could be a moon, it could be any kind of object.
You're thinking about like the rings of Saturn or something?
Well, no, I'm thinking of like all these different moons of Saturn. Is it possible that like these could have been like objects that came close and then got ripped apart, and maybe part of it fell, or like a majority of the object fell into Saturn, but then I don't know, maybe your outermost like got flung off from the rotation of the object.
Yeah, I mean, some of them are very rocky, right? When we think about these moons, which is really interesting, and some of them are quite irregularly shaped too. Like especially if we think about Mars's moons, right? They just look like junk, like piles of junk almost, like leftover debris from something quite catastrophic. Like I said, like science has been really allergic to catastrophism. That's a hard word to say. Catastrophism in the past. There's a long legacy of them fighting with religious fundamentalists about catastrophism, essentially. And so, again, it's also very difficult to. You want to tell a story that's generalizable as much as possible, right? So you want to be able to tell stories about planet formation and moon formation that you can generalize across lots of different systems. But if the reality is that there's black swan events happening in every solar system all the time that are unpredictable and bizarre, and you get the destruction of different planets, which leads to the production of moons, and it might be true, it probably is true, but how do you make a conservative story that you can apply to lots of different situations with ideas like that? It's also like you can't test them because you're never going to see that exact same thing happen again. You could simulate it. So some of my favorite work is done where people are simulating the production of planets and capture events and things that are really improbable but make a lot more sense than stuff just kind of happening uniformly in place. So I think that's just a really huge tension in planetary science, and I'm really excited about all these things because when I first studied astronomy, I just found these uniformitarian models to be really lacking. Like they seem okay on the surface, and you guys have hopefully gotten a good glimpse of it in your textbook and through some of the Moodle labs and stuff. Like there's a very uniformitarian story that's told, but there's problems when you push on a lot of that stuff. Especially, I think I've pointed out some of my favorite, or not, I don't want to say my favorite problems, but the most glaring problems. Like how do you create something as dense as the Earth? How's that possible, right? It doesn't seem to be possible. Nobody thinks that it's really possible when you push on the physics of it. Like getting a bunch of pebbles to turn into a boulder doesn't seem possible using gravity alone, right? So you can try to rescue that mechanism and come up with different ways of aerodynamic braking and drag, and you can maybe come up with a story that works eventually. But there might be more intriguing ideas, more evolutionary ideas that I think are really worth considering. And like I said, the Soviets took those quite seriously back in the 70s, and I think they're intriguing. They're at least worth considering. You have a system here that seems to naturally evolve a rocky core inside of it, right? These giant planets seem to naturally evolve things that look a lot like rocky planets inside of them. They build these little eggs inside of them, right? They also seem to, as they cool, develop complex chemistry approximating a lot of the molecules and stuff that we associate with our rocky planets in their thin atmospheres, right? But as we'll see next time, when we start looking at Neptune and Uranus are just big chunky versions of much more common types of those planets, which are smaller and seem to have lost a lot of their atmosphere and have even more complex molecules, waters, right, and ammoniums and carbon dioxide, and the stuff that we start to associate with Earth-like planets and with rocky-like planets, right? So, I think there's a really interesting metamorphic evolutionary tale to be told about planets changing across vast swaths of time, or maybe just changing through something like the hot Jupiter mechanism, where their orbit changes, they find themselves very close to a star, and it burns off a lot of their atmosphere, and what's left? A little rocky seed as the result of it, right? And so I think that's a really, really tantalizing story that has yet to be fully developed in the West, at least. But it does help me to at least come up with a plausible story for how you get something as dense as this rock we're standing on right now. Yeah.
So like with the idea that Jupiter is a brown dwarf, would that mean that it's a really old star and it like has just kind of burned out over time? So it's like become less bright?
So just to like, I think I understand the question, but I want to make sure because there's some terms. Like, so brown dwarfs are denser versions of Jupiter. Same composition, same elements, but they're denser. It's more atoms crammed into one space. Stars are the same exact composition of stuff, even more dense stuff crammed into them. What was the second part of the question?
So has it like,
Oh, the age, yeah.
has it like lost some of its material, like it with this theory that it's a brown dwarf?
Yeah, this is like the operant idea, the Soviet idea. Yes, so the idea, now, see, the Soviets weren't constrained by Big Bang cosmology, so they had no constraints on how long they needed to make these things happen, right? So if you take a star and you just stop doing fusion on it and you just let it sit there, how long does it take for it to cool off to the point that it looks like a Jupiter? And the answer is, according to at least like the most mainstream calculations I can find, it's on the order of like 1 trillion years. That's a really, really long time. That's, hundreds of times the age of the universe, right? Yeah, that's hundreds of times the age of the universe. Now, if like the Russians didn't care because they weren't into this Big Bang cosmology, so they didn't mind that they needed hundreds of times the age of the universe to make this theory work out, right? So yes, the idea absolutely was that as stars die and go dark and cool off, that eventually they evolve down into all of the different planetary types that we see. I mean, I kind of like open my mind up to the possibility that it can cut both ways too. Like if we do end up in the West moving the age of the universe back, and by the way, it seems like every new telescope we build, the universe gets older in terms of the redshift that we see for these galaxies gets bigger and bigger. The further we can see, the more we see stuff that looks pretty normal. And so it seems like that age of the universe is going to expand. How far will it expand? I have no idea. Now, like I was saying though, it seems like it could cut both ways. Like it seems to me like you might actually be able to form something like a Jupiter that is a failed star, or let's call it a brown dwarf, right? Because brown dwarfs are often called failed stars in mainstream parlance, right? They're not quite big enough. They didn't accrete enough molecule gas and stuff to make a star. But you might have two different pathways to the same object. We see this in biology all the time, by the way. So, bugs have wings and birds have wings, but birds didn't evolve from bugs, right? But they both converged on but they converged on the form of wing because having a wing turns out to be a really productive selective advantage and totally different paths to getting to the wing, right? So there seems, at least in my mind, I can hold both ideas in my head at once. It seems possible that you could have almost stars that look like Jupiters, and maybe in the operant idea you can have stars that cool off and turn into something that looks more like Jupiters. Maybe it can go both ways. I don't know, but it's a pretty out there idea. It's definitely not a mainstream Western idea. So. All right, well, that's it, guys. have a good weekend, and we'll do Neptunes and the whole trajectory of those next week.